So what I'm going to talk about today is, as I did explain in the abstract, pure category theory. The nice thing about it being pure category theory is that we can take interpretations in various settings. So in particular, the pure category theory can be interpreted as, say, logic and theoretical computing, or it can be interpreted as categorical linguistics and semantics, or it could possibly be interpreted as categorical quantum mechanics. Now, which of these I use to justify the category theory I'm going to talk about? The logic and theoretical computing is already well established. The categorical quantum mechanics, if there's any connection there, it's a remarkably speculative one. I might mention that at the end. And ultimately, a while back, I promised Manouche that I would talk about categorical linguistics. So today, categorical linguistics is going to be the fig leaf that's covering the category theory. And that's a metaphor I shouldn't push too far, I guess. Okay, so in particular I'm talking about the project to combine distributional and compositional semantics. So in distributional semantics, this is already an active field. The idea is that we can take a word and construct a meaning vector from it in terms of how it relates to other words. Two words can be compared using an inner product, and this is going to let us derive a notion of distance between two words. And the aim in bringing in categorical linguistics, is that our meaning vectors are going to be typed, and this is actually going to allow us to compare sentences. So, here's an oversimplified description of what the aim of the project is. We're going to assign words types based on their rules. This is going to be extended to sentences, which then become types by their grammatical structure. Our types, well, I take the definition of a type as an object in a monoidal closed category, or simply a closed category. Now, closed categories have a reduction or an evaluation, and our grammatical system needs to be chosen so that all grammatical sentences reduce to the same type. That's called S for sentence. And by reducing sentences to the same type, we can compare them in a fairly standard way. So, I don't really need to do this. We've seen plenty about monoidal closed categories in this conference. Only thing I'm going to point out that I think hasn't necessarily been mentioned so far is that they can be used to define an evaluation arrow. So something of type A tends to something of type A internal upon B. We've got an arrow that will go from there to B. This satisfies a sort of nice conditions, and I'd like to emphasise that this is actually an arrow within the category. So if you're working with linear maps, it's a linear map. If you're working with topological spaces, it's a continuous map. If you're working with reversible maps, it's actually a reversible map. Okay. So the kind of thing we want to do is to use typing and evaluation to reduce all sentences to the same type. So let's say we've got noun and an intransitive verb, the simplest kind of sentence we can have. We're going to combine these using the tensor, the monoidal tensor, to get noun, tensor, noun arrows S. And then we're going to reduce using the evaluation map, which is going to take us down to S. So this means that if we've got a more complicated sentence, we can reduce it down to the sentence type, and we can compare it to something that's much simpler, say noun, intransitive verb. So we can compare sentences with distinct grammatical structures. So, a few questions. First of all, how do we compare elements of the same type? In particular, how does this comparison relate to the monoidal tensor, the internal pom, and the evaluation? And what I'm trying to get at here is, what should the sentence type look like? I'm not going to give a complete answer there, but I'm going to say some structure that I think it may need to satisfy. And what I'm going to base this on is, does evaluation lose information? Which is going to be kind of a key point in the talk. Okay, well, category theorists have got a reputation for being abstract, so I'm going to base this on two concrete examples. Bobby loves Marilyn Monroe, and I like Fidel Castro and his beard. Everyone here has a good classical education. You'll recognise these as lyrics from Bob Dylan's songs. I'll find anyone who gets both the songs by the end of the talk. Okay, so these are going to be my example sentences. And back to some category theory. So an element of a type is simply going to be an arrow from the unit object of a monoidal category to that type. So if our noun phrase object is n, then Bobby is simply going to be an arrow from our unit object to n. Now, familiar examples, a member of a set, to a category theorist, it's simply a function from the one object set into that set. For quantum mechanics, this goes back to Dirac, a state is a linear map from the complex plane into a Hilbert space. Now, how do we compare elements? Well, how we compare elements depends on the form of categorical closure that we're using. So, we've seen Lambert pre-groups. These form a non-symmetric compact closed category. And if we're looking at the semantics, the distributional semantics is based on vector spaces, which is another compact closed category. So, as a tentative conclusion, I'm going to say we're going to work within a compact closed category, if only because this is also going to make the mathematics and the category theory a lot simpler. Now, compact closed categories, they're symmetric monoidal categories with a dual, which is a contravariant functor, and the internal HOM in a compact closed category, the A arrows B, it's got a very simple form, A dagger tensor B. Now, this is an awful lot simpler than the internal HOM with regard to other forms of categorical closure, and that's also going to be quite useful later on. Okay, so we're going to simplify things even further. Our examples are going to have self-dual objects, so A dagger is equal to A. This doesn't apply to arrows, so F dagger is not equal to F, unless you want the whole category to collapse to a triviality. So, how do we compare two elements? Well, Fidel is an arrow from our unit object to n, so is Bobby. They're both elements of type n. If we want to compare them, we start at our unit objects, apply Fidel to get to n, and then apply the dagger of Bobby to get back to I. And we call this the generalised scalar product, which is just a map from I to itself. Okay, well, why is this a comparison? Well, if we look at concrete examples, in various categories, the endomorphism monoid of the unit object might be the real numbers, it might be the complex numbers, it could be the unit interval, the sets, true, false, the natural numbers. Basic category theory will tell us that it's always an abelian monoid. And what we do when we take U generalised scalar product V is we're measuring the similarity or the overlap between two elements of the same type. Now, if we're working in vector spaces, this is of course simply the scalar product. Okay, now some points I'd like to emphasise at this stage. The unit object isn't the same thing as the sentence type. I'm going to do some illustrations, and we're going to assume that the unit object is the interval 0, 1, where 0 is nothing in common and 1 is exactly the same. I'd like to emphasise now, any actual values I give are just made up. Okay. Now, finally, we can compare any two elements of the same type. So we can't just compare elements of the sentence type, we can compare any two elements provided they're of the same type. Okay, so let's go back to our sentences. Bobby loves Marilyn Monroe, I like Fidel Castro and his beard. Well, we know these are both Bob Dylan lyrics, so we're going to replace I by Bob Dylan, and we're going to change the verb from the first person to the third person accordingly. Okay, well, now we're going to make an estimate. They're both of type n, noun phrase, so we can form their scalar products. Let's say, these look pretty close, we're going to say 0.98. Okay, now, already we're making, does this work? Yes. Already we're making a mistake. From the context, we've assumed a match between I and Bobby. If you look at the wider context, then it appears that Bob Dylan in this sentence was actually talking about Robert Kennedy rather than himself. But this isn't apparent from the sentences, from the songs themselves, it's only apparent from the wider cultural context in which these songs are set. So already we're starting to make one mistake. Okay, now back on firmer grounds, we want to compare likes and loves. These are both transitive verbs, so they're of the type where you take a noun phrase, and this gives you something that takes a noun phrase and returns something with sentence type. Well, Manouche has already given us a value for this. I assume that's also made up, but the overlap between likes and loves is 3/4. Okay, now one last comparison, and this one's going to be a touch more difficult. How do we compare Marilyn Monroe with Fidel Castro and his beard? Okay, well, at York, somebody would take a very pragmatic view of things, and they say if you want to compare two noun phrases, you just type them both into Google and count the number of page hits. That's not the approach I want to take here, for obvious reasons. But even if we take a more structural point of view, they don't have the same type. Marilyn Monroe has type noun phrase, Fidel Castro and his beard has type noun phrase, tensor connective, tensor noun phrase. So, okay, the fact that it's and isn't particularly relevant. This could be and, it could be or, it could be exclusive or, I like exactly one of Fidel Castro and his beard. You can keep going with this. So, what do? Well, we type our connective. We want this to reduce to something of type n. So, we want n tensor something tensor n to reduce to n. So the connective type has got to be n arrows n arrows n. You agree with that, don't you, Samson?
I'm sorry, I can see where this is going.
You can see where this is going. Okay, so what we can do now, well, we can apply an evaluation map to Fidel Castro and his beard to get something which is simply a noun phrase. And we can then compare this to Marilyn Monroe and, well, this is just a guess, but I'm pretty sure that the overlap between Fidel Castro and his beard and Marilyn Monroe is and always has been 0. Okay, now I'm going to take a digression. We've got our connective type, n tensor c tensor n is to evaluate to n. So noun phrase and noun phrase has got to evaluate to another noun phrase. And the problem here is that, well, these connectives, they don't just apply to noun phrases, they're used more generally. So we could have Bobby loves and obeys Marilyn Monroe, Castro's big and bushy beard, or Bobby likes Marilyn and I like Fidel. And the appropriate typing at this point is x arrows x arrows x, but x is going to vary according to the context. So, well, if you want a logical system in which to type this, we need to consider parameterized types if you're a follower of John Reynolds, or polymorphic types if you're a follower of Jean Gillard and Company. So I'm going to abuse notation slightly, and to emphasise that x is simply a variable here, I'm going to write lambda x with capital lambda to emphasise that this is a type variable. And of course,
like polymorphism is not a term due to Girard, it goes back to Strachey at least.
it does, yes.
Since we're in Oxford.
But system F, we do need to attribute to Girard, I believe.
Yes.
Okay, well, I'd like to say that this is simply notation, but in Steve Clark's talk he mentions type lifting. So we have to take this idea of lambda calculus with, and in particular polymorphism, a touch more seriously. And I'm going to say that this is going to allow me to identify this type with the alternative type x tensor x arrows x. So this is pretty much a defining equation of the order declension in a category. Okay, well that's the end of the digression. Let's get back to comparing our sentences. So here's some simple category theory. If we're given scalar products a, b and x, y, how do they interact with the tensor? Well, they interact in pretty much the simplest way that you can imagine. A tensor x, b tensor y. Scalar product is simply the scalar product of a and b composed with the scalar product of x and y. This is a general categorical identity. It's not just something about coordinate spaces or vector spaces or whatever. It holds generally. Okay, well, let's try and compare our sentences. We've got Bobby, Bob Dylan, loves and likes, Marilyn Monroe, and Fidel Castro and his beard. And what we're going to do, well, we've got two sentences of the same type, and we're just going to take their inner product, and we get 0. There's no overlap between these sentences. Okay, now I'm going to pause at this point, mainly because I need to drink. I'm going to ask, is this the correct thing to do? What we've done is we've compared L1 and L2 at a certain level. We've compared them as elements of this type. Are we going to get the same answer if we compare them at this type, or if we first reduce them to the sentence type S and then compare them? What I'm really asking is, does evaluation preserve scalar products? So let's say we've got elements x and y of type G. We've got an evaluation from G to S, and by composing we get elements x prime and y prime of type S. So, is it true that x scalar product y is the same thing as x prime scalar product y prime? Okay, answers? Yes, no? No, it's not. It's definitely not the same. The simplest possible example comes in quantum mechanics, where evaluation is partial measurement. Partial measurement most definitely does not preserve our inner products. Evaluation is an irreversible operation. So, is this a bug or a feature for categorical models of meaning? Well, being a former programmer, I've got to insist it's a feature, it's not a bug. But I'm going to try and justify that. So my justification is going to come from scruffy cats. So let's say we've got distributional semantics for cat, and this is going to be a vector that provides information about cats in general. And this, another element, scruffy, adjective type, say n arrows n, which is going to tell us about the general concept of scruffiness. And then we're going to take the tensor product of these. This is going to tell us everything about scruffiness, along with everything about cats. Now this is simply too much information. We don't need to know all about scruffiness. Scruffy cats, scruffy dogs, scruffy logicians, the whole works. Same, we don't need to know all about cats. Big cats, small cats, scruffy cats, cats in hats, compact closed cats. We don't need to know all this information. So, when we compose with the evaluation map, we get a new element, and this new element is going to tell us about scruffy cats only. And it's absolutely vital that evaluation can forget information. Okay, now if you want a more structural point of view that isn't necessarily based on scruffy cats, you can say we're working with compact closed categories and take a logical view of our type system that is a degenerate fragment of linear logic, which is resource sensitive. So the resource, say scruffy, is consumed in this evaluation. It doesn't play any further role in our sentence. Okay, well, we don't have reversibility in that sense. Have we got a limited form of reversibility or preservation of the scalar product? So let's say we've got cat and dog. Are we going to get the same result if we look at scruffy cat and scruffy dog as we do when we compare cat and dog? Again, no, we're not. So I'm going for a categorical explanation of this. Our elements of type x arrow y are in one-to-one correspondence with our arrows from x to y. And most elements, of course, do not correspond to isomorphisms, never mind inner product preserving isomorphisms. So if you look, another example from quantum mechanics, if you look in the book that Bob has had out recently, we see a proof of this statement that if we've got an element of type h tends at k, and we use evaluation to map this to the arrow from h to k, well, our arrow is unitary exactly when our element, our quantum state, is maximally entangled. And this is a very, very special condition. Okay, so to take things a little bit further, do we always want evaluation to lose information? And no, we don't. So we've already seen an example of this. Fidel Castro and his beard. So we're going to have a single arrow. When we evaluate this, we don't want the compound noun phrase Fidel Castro and his beard to lose any information about Fidel Castro or any information about his beard. It's an evaluation, and the arrow named by and has got to preserve the inner product to be reversible. Hello.
Because you mentioned problem. In fact, the type in the one you wrote down, you make a conjunction on a partial not verb phrase. In fact, either.
Sorry.
The type here.
Yes.
Is not the one we would use in linguistics.
Okay.
You would use another type which would not avoid this problem. I love Fidel Castro and omission. I love his beard.
Okay.
This would be the type would reflect this.
Okay. It's going to be very reflective, yes.
That's what you are aiming at, right?
Yes, yes, yeah. Yeah. Okay, so that's a kind of toy example. A more serious example is what happens if we apply this to sentence type. So if we take, say, I don't know, sketches of an elephant or War and Peace, and go through this and replace every full stop by and, then we get something that is a grammatical sentence, albeit one that you really, really wouldn't want to try and analyse. But at the same time, we don't want this evaluation to lose information about either sub-sentence. So, if we're going to say that we're going to carry on with this approach in semantics and say that the arrow names by and, well, it's got to be a monomorphism. And, well, it seems that whenever we have a polymorphic type, we want something of this form. So, now we need to look at how, in logic, we build models of polymorphic types. So, what we need, as a minimum, is an embedding from the endomorphism monoid of S tensor S into the endomorphism monoid of S. So, a way of saying this is that S contains a copy of S tensor S. Now, I'm going to look at a special case where this is an isomorphism. That's not a major problem, mapping between the two situations generally. Occasionally it might cause problems, but in most situations we can map between the two. In terms of the linguistics, to say that this is an isomorphism rather than an embedding, I think that we simply need to admit the possibility of sentences that are completely content-free. Okay, well, let's look at a distinguished subcategory of this. Let's look at the subcategory generated by S, which is isomorphic to S tensor S, our unit object, and the tensor product. So we're going to build up all possible tensor copies of these things. Now what we're going to see is that S tensor I is isomorphic to S, S tensor S is isomorphic to S, and the internal HOM of S and S is S dagger tensor S. S is self-dual, so this is S tensor S, which is of course isomorphic to S. And what we have here is a compact closed category where all our objects are isomorphic. Now, I'd like to emphasise that...
contain the unit though.
Well, no, I'm going to... The unit's there for a reason for the moment.
Yeah, but it's not... Oh, alright.
Yeah, yeah.
Not that close.
Okay. You're entirely correct, as always. Okay, first of all, I'd like to emphasise that these are sort of bizarre categorical abstractions that no one's ever going to consider. Simplest example, well, 0, 1, 2, 3... That's a 7. Okay, now the natural numbers, of course, dating back to Hilbert, is the notion of a hotel with a countably infinite number of rooms. Now two countably infinite coach loads of people arrive at the hotel, and how do you fit them both into the hotel? Well, the first coach load, you put them in the even numbered rooms, and the second coach load, you put them in the odd numbered rooms. So these aren't complicated things, they're simply, well, things like the natural numbers. Okay, so where am I going from here? Good question. Well, first of all, I'd like to point out that isomorphisms from two copies of the natural numbers to one copy of the natural numbers, they're not unique. Hilbert's hotel is probably the best known example, but if you look in detail, there's a correspondence between isomorphisms from n tensor n to n and points of the Cantor set. So there's actually rather a lot of these things. Now, back to Sanson. We're looking at this subcategory and we can't assume strict associativity. Associativity has got to be up to canonical isomorphism. Now, before people object that this contradicts Maclane's coherence theorem, it's actually quoted in Maclane's book immediately before he introduces the coherence theorem. And he says that trying to combine these two notions, self-similarity, S is isomorphic to S tensor S, and strict associativity, well, S tensor S is equal to S tensor S tensor S. These force S to collapse to the unit object. Now, if you look at the proof of this in Maclane's book, it's due to John Isbell, and, well, it is a kind of ad hoc proof. So what I'd like to do is give a sort of more structural explanation of why that holds. Okay, so let's take this category built up from all possible tensor copies of S, And as Sanderson said, we're going to knock out the unit object because we really don't want that there. Okay, so no unit object. Now let's take some arbitrary object. Let's take a pen that works. Let's take an arbitrary object, k, of this category. Now, simply by the way the category is defined, k is isomorphic to S tensor k, which is, of course, isomorphic to k tensor S. Now, this looks kind of familiar. So, the question is, why is S not the unit object for this category? It's not because it's the natural numbers. Okay, the reason it's not the unit object for this category is that if you look at the isomorphisms exhibiting this, they don't satisfy the coherence conditions for the unit isomorphisms of a monoidal category. They don't. Unless, of course, you say that our associativity is strict, in which case they do. In which case, where you did have the natural numbers, it collapses to the unit object for the category of natural numbers, sorry, for the category of sets and functions. So this is why we need non-strict isomorphism sometimes for associativity. Okay, so now I'm going to take another digression. And this is going to be for logicians and category theorists, but it should be interesting anyway. Okay, so let's take this category without the unit object and look at the identities S, it's isomorphic to S tensor S, it's isomorphic to S internal upon S. This looks like the defining equations for a C monoid, which is a Cartesian closed monoid without unit, or indeed a model of the untyped lambda calculus. We can take this analogy seriously, and what we see is that any object of this subcategory is actually a compact closed monoid. It satisfies all the axioms for a symmetric monoidal category with a form of categorical closure that looks like compact closure.
What is Cartesian about this?
Oh, nothing's Cartesian about this.
Ah, you say Cartesian closed monoid.
No, I say it looks like the defining equations for that. If we had product there rather than monoidal tensor, then it would be a C monoid. It's not. Okay, well, I'm just going to go through a little bit of the structure of this. So, we've got a monoidal tensor, which is, of course, a monoid homomorphism that takes two copies of the same homomorphism monoid to one copy. And this is defined by the convolution. So we go from S to S tensor S, using our isomorphism delta. We look at F tensor G, and then we map back to S, using the isomorphism nabla, the dual delta. And, well, this is associative up to isomorphism, it's commutative up to isomorphism, and of course there's no unit object. Okay, so the associativity isomorphism, well, let's call this T delta, just to go with the tensor subscript delta, and this, well, this satisfies the conditions that you want it to satisfy. It maps right associated to left associated arrows, bracketings, and it also satisfies MacLane's pentagon condition. So it's a genuine associativity isomorphism. We can write down a coherence theorem for this. Now, it also satisfies a very natural interaction with the associativity isomorphism of the category in general. Okay. Are you doing okay for time?
Another 5 minutes.
Another 5 minutes? Okay. Oh gosh. Okay, now we've also got a symmetry isomorphism. This again satisfies what you'd expect for a symmetry isomorphism, and it satisfies the Plain's hexagon condition. And it's got a nice interaction with the symmetry isomorphism of the larger category. It's simply the convolution. Okay, well, end of digression, you'll be pleased to know. So, let's go back to track. Back on track.
Those isomorphisms are language around things for the geometry of interaction.
They are indeed, yes. Okay, so I haven't gone into details of how we build models of polymorphism in categorically, simply because this is a half-hour talk, not a lecture course. But as a very brief summary, what happens is, well, first of all, you destroy all your types, and then you have an untyped system, and on top of this untyped system, you build new types that you have more precise control over. It's a kind of year zero sort of thing. You annihilate everything, and then you try and rebuild on top of that in ways that you can control more precisely. Okay, but what I'd like to say now is that I've been using some fairly suggestive notation. we've got delta from S to S tends to S, nabla from S tends to S to S, and we're also assuming that nabla is the inverse and indeed the dual of delta. So the question is this a dagger Frobenius algebra? Let's have a look.
So, you used the dagger before to denote the transpose.
I'm sorry, I'm treating it as the dual of the category.
Yeah,
Yeah.
okay, okay.
But it's
Yeah.
identity of objects,
Yes, it is. Yeah.
so it's the same. There isn't a distinction between the star and the dagger.
No, sorry.
No, I know, but I think
I'm-
that's the answer to Bob's question.
Yeah.
Yeah, but because of Frobenius algebra in that sense is always dagger.
Okay,
It gives
that's
its own
cool.
transpose.
Okay, that would shorten my proofs. Okay. Okay, so, well, this is going to fall down at the first step because there's no natural candidates for the units. Fortunately, yesterday Samson redefined Frobenius algebra to be without units, so, okay, cool, we can carry on. Okay, how about associativity? Well, again, we've seen that if we have associativity, strict associativity, everything's going to collapse. So we can't have this equal to this, simply because, well, they don't actually start at the same object, these arrows. That's kind of unsatisfactory. What we do have is associativity up to isomorphism. So if we're going to add in canonical associativity isomorphisms, the one object associativity isomorphism tests, and the usual associativity isomorphism in the larger category, well, the appropriate diagrams do indeed commute. Delta, 1 tensor delta, and delta, delta tensor 1 are the same thing up to canonical associativity isomorphisms. Okay, well, we've got what I like to call lax monoids and comonoids, assuming we don't care about the units. So I'm going to call these unitless monoids and comonoids, even though strictly a monoid without a unit is a semigroup. But for some reason, category theorists seem a touch biased against semigroups. They always like to have an identity on everything. Okay, so the Frobenius condition, does that hold? Well, what this says, I'm going to read from left to right here, what it says is that this composite has got to be the same thing as this composite. I'm not going to bother with the right-hand version of this, simply because we are assuming symmetry. Okay, well, no, again, but it fails for unsatisfactory reasons. And the reason is that we're assuming strict equality on the right-hand side here. So let's replace strict equality by canonical isomorphisms, and we discover that actually, yes, assuming that we don't mind having all our equations up to canonical isomorphism, then the Frobenius condition is satisfied. To prove these, well, I've already got all the diagrams up, you simply paste them together where edges match. It's jigsaw proof, basically. So, well, we've got a unitless dagger Frobenius algebra up to canonical isomorphism. Anything else? Well, we've got commutativity and co-commutativity, again, up to our canonical isomorphisms. And finally, we've got what some people call the classical structure condition, which is that nabla composed with delta is the identity at, and that should be S. And this was our starting point. So, all we've done is we've gone from this polymorphism condition, which should really be called the untightness condition, and we've used this, and this leads to a lax, unitless classical structure, which is the kind of thing that's used in categorical quantum mechanics to specify an orthonormal basis. So, okay, the question here is probably what the hell is going on here. Is it the case that by allowing for laxness, associativity up to isomorphism, we've simply pushed the definitions too far, we've broken them, they don't actually mean anything? And I thought that for quite some time, but then I was looking at playing about with something called the dynamical algebra, which dates back to the late 80s, early 90s, used by Danossovenier, Girard, etc., in logical models. And this is an example of what I was talking about earlier, a one-object compact closed category. Now, people who are familiar with it will know that you can have matrix representations for arrows in this algebra. Now, these matrix representations aren't unique. So what determines them? Well, I was looking at what determines them, and I discovered that actually they're in one-to-one correspondence with points of the Cantor set. So there are actually rather a lot of them. And indeed, they are determined exactly by isomorphisms from 2 copies of n to 1 copy of n. So in that particular situation at least, these lapsed unionless Frobenius algebras are behaving exactly the way that they behave in the more familiar setting of specifying orthogonal bases in finite-dimensional quantum mechanics. And they're allowing us to talk about matrix representations, bases, changes of bases, etc., etc., etc. And I think I'm pretty much out of time here, so that's my conclusion, but I'd like to leave the real conclusion to the master himself. Okay.
Well, we've got a bit of time to spare. Do we have 3 minutes of questions? And then go and get some Anyone got any questions?
Can you say a bit about how the result relates to the original linguistic interpretation?
Yes, the original linguistic interpretations of Debrief. Okay. What I'd say is that as soon as you allow for polymorphic types, or things that behave like just and sticking 2 sentences together, and you require that doesn't lose information, then you immediately find yourself in this setting. I didn't actually bring in anything extra at all. It just comes naturally from that one starting point. Hello.
So if you do that, would you end up getting a non-zero correlation? Because at the beginning you were talking about how you multiply these things together and you get a 0 correlation, but it changes once you start evaluating it to a sentence before you do the valuation. So if you were going to do the run through the imaginary numbers again at the end, would it give a non-zero value, or would it?
Okay, that's actually touching on a very deep point. The question is, because to do all this we had to knock out the unit objects, and that implicitly knocks out the notion of comparison via a generalised scalar product. So, no, that's a good point. So there may well be ways of comparing, but this is actually a sticking point for that at the moment.
Steve?
I just had a response to Anne's point about the interpretation of the noun phrase, and pointed out that you could interpret it distributively in that case. But that's not always the case. So if you've got something like John and Mary met in the street, you can't interpret that as John met in the street and Mary met in the street. So your point would go through for those.
That is interesting to know, thank you.
I come back to the sentence. Okay, the normal type, if you give the X there for your conjunction, would be N to S.
Okay.
N to S. What I would like you to know, if you make X equal N to S, would you still lose your information or not?
Okay, I'm not a sort of natural born linguist, so that's something I would have to think about.
But S equals N to S already gives you an interesting reflexive equation.
It does indeed.
Because you have the recursion of the contravariant part, which is the difficult thing.
To give you something similar, but probably not the same. Yes.
Alright, maybe one last question.
I was wondering about the zero in your scalar products. Would you really like to have zeros, for example, by Bayesian setting? You would disallow the values 1 and 0 because that actually kills learning on the higher. And also here it seems that your zero is rather a dangerous concept, because it kills the whole rest of the
zero in the
as a value of your scalar product.
That's true. I simply wanted that because I wanted to eliminate any possibility of an overlap between Lowell and Monroe's Castro. Yes.
It was a feature, not a bug.
Thank you, sirs.
Alright, so we come back at 55 and move things a bit, just have half an hour for that chat. Alright, back at 55.